Hello, my name is George, and today I'm going to talk to you about embedded audio policies with WirePlumber. So let's start by defining some terms. What is a policy? A policy is a set of rules. Usually, when you hear the term policy, you think of the security perspective. So you think about access control, things that are allowed or disallowed. That's usually the policy. In the context of the audio system, though, there are a couple of more things to consider. A policy in the audio system context is also a set of rules for routing audio streams towards devices. So you have a stream playing. Which audio device should it target? Which speaker? Which microphone? You have rules for arbitrating between streams. So let's say you have two or three or four or five players playing music at the same time. What should happen? Then you have also rules for configuring streams and devices. So let's say you have your laptop, you are playing something, and suddenly you decide to plug in a USB sound card. What should happen at this point? You need some kind of rule to decide what will happen and how this device will be configured, what it will be used for, what kind of sample rate it will use, what kind of buffer size and things like that. Now, what is an embedded policy? Now, this is me basically stretching the term embedded. It's not really something suitable for all embedded systems. What I'm referring to as embedded policy is basically a use case based routing and arbitration, sometimes also referred to as the role based policy. So this is the policy that you typically find in your phone or your in-vehicle infotainment system on your car, where each stream is assigned a role, it is assigned a use case, and based on that use case, the system behaves differently when this stream comes. So for example, on your phone, if you're playing a video, you hear the audio of that video, but then as soon as a notification appears and you hear the blink, then the video suddenly ducks and you hear it on a lower volume because the notification is quite important for you to hear. Or if you have a phone call, then everything stops and you take the phone call. This kind of policy is what I'm talking about here. So let's discuss what is the difference between this use case-based policy and the standard policy that you have on a desktop system. On a desktop system, there is no such thing as a use case or a role. You have applications such as a web browser, a music player, or a voice call or video call application, and they just link directly to devices. So you typically have a user interface where you can select the device you want to use, the speakers you want to use and the microphone you want to use. You can configure it either for the entire system or you can configure it per application, at least on Linux, because on other systems like macOS, for example, doesn't have this option. But yeah, on Linux you can select it even per app, but it's usually not used. It's something that you select for the entire system, and all the applications will target that device. And there is no other kind of rule. So if you have your music playing and you start a video call, the music is still playing. Nothing changes. You have to manually go and stop it. Now, on a use case-based setup, every application, every stream that comes from an application will be assigned a use case or a role. So your navigation application in your car, for example, will be assigned the navigation role, the music application, the music role, the voice call application, the communication role. And then, based on that role, the applications will link to a different device with a specific set of rules. And it could be, so the device where they will link could depend on the use case or the role, or it could be something configured for the entire system as well if there is only one choice. Now let's discuss what are the components of such a use case-based policy. The first component is associating streams with use cases. So you need a set of rules that will tell you what use case each stream belongs to. So for example, if you have a music player app, it belongs to the music use case. But how do you know? You need some kind of heuristic to understand that, oh, this is my music player, so I will assign it the music role, and I will treat it as music. Whatever comes out of this application is music. Similar for other roles. Then a second set of rules, another component of this policy, is associating the use case with the hardware. So which speakers or microphones should be used for each use case? Typically, there is only one choice, like one set of speakers and one microphone. But it is much more common, at least in automotive systems, also in phones, that you have a hardware DSP. And the idea there is that each stream should be forwarded to the DSP as it is. And the DSP will then have its own set of rules to mix those streams, or mute one, let the other play, and things like that. Or apply filters, like for example, if you are playing, if you have a voice call and you tell the DSP that this is a communication stream, it will apply echo cancellation by default, for example, things like that. Now, forwarding to a hardware DSP can happen in two ways. One way is that the DSP would expose different ALSA devices for each stream. So then it is a matter of mapping. Every application stream will map to a use case, and then every use case will map to one ALSA device. So that is the example I have at the top. So the navigation use case maps to this ALSA output device 1, and there's that. The DSP will take care of the rest. There is the other way, that is, you have one ALSA device with a lot of channels. And each pair of channels, or every few channels, a group of channels, let's say, is meant to be a different stream. So at this point, you have to configure this device as a multi-channel output device or input device, and then split groups of channels for different roles. Here I have an example where I have one device with front left, front right, rear left, and rear right channels, and then the two front channels are basically meant for music, and the two rear channels are meant for communication. That doesn't mean that they go at the rear of the car. It's just a way for the audio DSP to communicate with the user space. A bit awkward, but that's how it's implemented. Finally, there's a third component in that policy, and that is the arbitration between use cases. So let's say you have a navigation instruction coming out of your navigation app while there is music playing. What should happen? Typically, something that many systems do is apply a volume DAC for the music. So the music suddenly drops volume by, let's say, 30–40%, and you hear the navigation instruction clearly, and then the music ramps up again, maybe with a nice curve, so that that doesn't go suddenly up or down. You have a nice ramp up and ramp down. Or another arbitration case would be to, let's say, pause the stream, pause the video, pause the music, and make sure that whatever else is coming is heard without any noise in the background. Now, how all of that could can be implemented with WirePlumber. First of all, what is WirePlumber? WirePlumber is a session manager for PipeWire, or as I prefer to call it, an orchestrator. So session manager is a bit of a controversial term, especially for people that are coming from a Jack background. WirePlumber is basically something that takes control of the entire PipeWire graph and makes sure that nodes are linked appropriately and configured appropriately, and basically controls the entire thing. WirePlumber is developed and supports both desktop and embedded use cases. So in this talk, I'm talking about an audio policy which is specific to some embedded systems. But of course, there is also the standard policy that we apply on desktop, which resembles the PulseAudio policy that we had many years ago. It is a heavily modular and customizable daemon. The policy is implemented in Lua, so there are Lua scripts that do all of that. And it's easy to plug into that and write your own Lua scripts to alter the behavior in some ways. Especially with the latest updates that we did last year, where we now have a fully event-based architecture. Basically, whatever happens on the PipeWire graph is a new event, and then you have callbacks for that event, and you can chain callbacks, so you can have multiple scripts that chain to the same callback, to the same event, and each of them will take an action or arbitrate between those callbacks what should happen, and something like that. So about 6 months ago, we released WirePlumber 0.5, and with 0.5, a few months later, actually in July, I don't remember exactly when, we merged this role-based policy, which fully replaced the endpoint-based policy that we had in WirePlumber 0.4 and previous versions. Now, if you don't know what the endpoint-based policy was, never mind. It was something a bit more complicated. Originally, when we attempted to address, the automotive and mobile phone specific policy, we thought of a design that was a little bit different in direction than what the PipeWire author Wim actually wanted to do for the desktop. So kind of we found ourselves like trying different things in both what's the right word? So I was trying things for embedded, and Wim was trying things for desktop, and we thought that we would converge, but then we didn't exactly converge, and we started iterating on those designs, and we finally reached a point, like on my side, I reached a point where I said, okay, this endpoint-based policy doesn't make sense anymore. We should simplify and make it easy for people to use, because that was complicated enough. Anyway, one of the complications that this endpoint-based policy had was that it didn't allow combining with a standard desktop policy. So if you wanted to use a role-based policy on a desktop system, you couldn't. Now, with the changes we made here, it is possible. And maybe it's something that the desktop designers could consider, because it can make sense on a desktop system as well sometimes to have arbitration based on use case. So it's something possible. How are the use cases implemented? Very simply with loopbacks. Every application links to a loopback, and then the loopback links to the ALSA device appropriately. There are different sets of scripts, Lua scripts, that implement the application to use case mapping and the use case to hardware mapping. So they can change independently and makes things easier as well for customization. How are loopbacks implemented in PipeWire? They are typically two coupled streams. One input stream, one input node, and one output node. They appear as different blocks on the PipeWire graph, but they are in fact coupled underneath. So whatever goes into the input actually comes out of the output. Without that being visible somewhere on the graph. So if you're using some kind of graph inspection tool, you will see two different nodes, two different blocks on the graph. But in fact, they are interlinked underneath. One of them registers as a target or so-called device node. So it appears as if it was a device to at least it's not a device, but in the PulseAudio terms, it would have been a device. It's something that you can target and send audio to when you're streaming out, or capture from if you're grabbing from a source, from a microphone. The other stream, the opposite direction stream, will register as a stream. So it is registering as if it was an application stream and has to be linked somewhere else. The example here, the first node is the input node is an audio sync, that means a device, and the other one is a stream output audio, so it's a regular stream as if it was an application. Now, the part that associates application streams to use cases works like this. The application is expected to have a property that is called media role, and that property will have the value of the role, the use case. In this example, the media role of this music application is simply music. There is, of course, the problem that not all applications, in fact, very few applications do apply that property, to set that property. So how do you manage that? Well, fortunately, PipeWire has the ability to configure those properties also with a set of rules. So you can go into a configuration file and have and match certain properties of the application. So let's say you can match the application name or application ID if you have some sort of identification on your packaging system, and apply another property. So in that case, you can apply media role for whatever. There's some cases where you want to have even more complex decision making, and in that case, you can use also the scripting capability of WirePlumber. Therefore, you can write a Lua script that executes when this application node appears. And that script could call into other resources on the system. It could use, let's say, dbus or a socket to talk to something else and figure out what this application is. So if you have an application framework on your embedded system or a security framework that understands what each application is, that this can work. So you can categorize applications this way. And then the loopbacks are meant to have this device.intendedRoles property, which is an array, and it takes all the roles that should be associated with that specific loopback. So WirePlumber, as soon as it sees that an application has the media role property, it will look for other targets, like target nodes that have this device intended roles property. And as soon as it finds a match where the string matches, it will make that connection. Why is it called device intended roles? That's for compatibility with PulseAudio, because that thing actually existed in PulseAudio, and I just wanted to make sure that it keeps working as it was in the past. Now, for associating a use case to the hardware, we just use the standard policy. So the other end of the loopback, as I said before, is just a regular application stream. So as soon as it appears, WirePlumber can just use the standard policy and link it to the default output. In the first example here at the top, I have this music loopback out, which has a media role of loopback. Now this is on purpose. The loopback role on the system where I have configured this does not exist in any of the device intended roles properties on any other target. So if the target is not found by role, then WirePlumber falls back and goes to link to the default output. In the second example in the middle, the loopback output has a target.object property, which is explicitly specifying which node to link to by name. So the also sync would have a node name property, and these two matching, the WirePlumber will make that link. And finally, for the weird DSP use case where you have channel splitting, you could also do the same with target.object, but also configure linking to specific channels. So there you can see that the last loopback has an audio position, rear left, rear right, and that means that it will be configured to link to those channels only from the target. So this is standard policy. It works. Of course, on a production system, you may want to customize. So this is where WirePlumber comes in and allows you to use the Lua scripting mechanism to customize this if you want, or you can use some predefined rules with some JSON configuration to make all of that work. Last but not least, arbitration between use cases. So in the case where you don't have a DSP and you want to do everything in software, there is another Lua script basically that manages links to manage the nodes, the use case nodes. So it looks for all the nodes that have this policy role-based target equals true. This is a property that is typically set on the loopbacks, the loopback targets. You see here, I have this set on my music loopbacking. It knows which nodes have this, so it knows that these nodes are actually use case targets. And as soon as a link is made to that target, then that link is managed by a special script which has some extra rules for arbitration. And the rules are basically that each role has a priority and has an action. And the action can be mix, cork, or duck. So mix meaning that the two links will just continue to exist together and the audio will be mixed. Cork is that the higher priority link will be audible and the other one will stop. So that stream will be stopped temporarily. And duck is the higher priority stream will play at full volume and the lower priority streams will lower in volume. These priorities and actions are configured directly on the loopback nodes. So the same node that has the policy role-based target property can also have some extra properties to define the priorities and actions. And yeah, the highest priority wins, the lower priorities follow the action. Now, in the case where you have a hardware DSP, you don't want that. You want to stream everything to the DSP, and the DSP will take care of applying those policies. Even though you may want to combine with some actions on the software side. For example, the cork action can be useful because you want to stop the stream also on the software side. You want the player that produces that music stream to be aware that it has been corked and not just stream things that get dropped on the DSP. And that's possible to do. So it's possible to use a mix of those implementations. But yeah, it's also implementation dependent. You can always drop your custom Lua script to implement this. Here's an example of how it looks on a software-based arbitration mode. So these, we have two applications, and then we have the loopbacks, one for music, one for navigation. And you can see that the input nodes of the loopbacks have the policy role-based target equals true property, and that means that the links that go towards these loopbacks are going to be managed by this policy. And the priorities and actions are encoded directly on the properties of those loopbacks. And on the other end, it's as usual, no special properties, they just link to the ALSA sync. On a hardware DSP arbitration, yeah, you don't have that. You don't have these properties, so there is nothing happening on WirePlumber. All the streams just get forwarded directly to the DSP. And here I just have an example where I show how two different streams get forwarded to the ALSA sync on different channels. So music goes to front channels, navigation goes to the rear channels, and the DSP takes care of the rest. Now, you may ask, why loopbacks? Why do we have the loopbacks in the first place? Because, I mean, if we are, let's say, directing streams to ALSA directly and let the hardware DSP do their work, why have the loopbacks in the first place? So for the software-based arbitration, we actually use the loopbacks to implement volume control. And this is the reason that we introduced those loopbacks in the first place, because we want a way to have volume control per use case and not per stream. So you can have multiple music applications that go to the same loopback, and then we can control the volume of all of them as one thing. And for the hardware DSP use case, the loopback is very useful to do the remapping, right? To do the remapping of the channels if you have such a setup. But it is optional. Like if you have a DSP that exposes one ALSA sync per use case, you could actually go and place that device intended roles property directly on the ALSA sync and skip the loopback. It's not useful to have the loopback in that case. We can also have the priority and actions properties directly on the ALSA sync, and also use the arbitration policy directly with the ALSA syncs and skip the loopbacks. If we're not doing channel splitting, then it's not worth it to have the loopbacks, or if we're not doing volume control. So that's pretty much all. The next steps on this is, first of all, to improve the corking. Something that is currently missing, and it's been known for years, we just haven't gotten around to fixing it yet, is that when we cork a stream, when we pause it temporarily for something else to play, we need to inform the application that this has happened. Currently, we don't do it. So the application currently, what happens is that it thinks it's playing, but its clock is not moving. So it pushes something, and the audio clock is like frozen. So in GStreamer, in GST PipeWire sync, we also have some detection mechanism when this happens to actually send a signal to the application to request state change. So the application can change state at this point, but then when the application wants to request the change to go back to playing, there is no way to signal that back to PipeWire. So the user may click there and nothing happens. The other thing that it's interesting is to do the DSP management. So currently, if you're using a hardware DSP, typically you have a different application which is doing the management, the orchestration of the DSP. You configure all the streams that you have, the roles, the actions on a separate application with a separate API. It's a bit of a pity because we have this infrastructure in WirePlumber and we could be doing it in a more unified way. Of course, the problem is that each hardware DSP vendor has different APIs and different configurations, and it's hard to bring that all upstream. And there are often companies that come and ask me, like, how can we bridge that DSP to PipeWire? And I'm like, I don't know. Look at the documentation. Ask the supplier. I don't know. But it would be nice if we could have a unified API. So if you if anyone has ideas there or has contacts or whatever, talk to me. Of course, one thing we can do in that area is try to work with the Sound Open Firmware project, which already does DSP management for some DSPs with an open source firmware and open API. So I'm actually looking into that. I want to try and see how far we can go with that kind of thing. That was all. Thank you.